Okay, we are recording it. Please start.
Okay. So hello everyone. Today I'm going to present the paper from ACM.
TOSEM, actually a TOSEM journal. So this is one of the top journals in the field of software engineering.
Okay. So the paper name is Modular Tree Network for Source Code Representation Learning.
Okay.
And here is some background for the authors of the paper. And we can see some familiar names like Li Ge, Xinxia, and Zhijing. And most of them are from Peking University, and I think Xinxia is from
Monash University.
Monash, yeah. And before we go into the papers, let's do some background. Because for the last paper I already elaborated, so I will quick go through those background. So code command generation. This paper, the research problem of this paper is one of the research of this paper is to do the code command generation. And code command generation is aiming to automatically generate natural language descriptions for source code. And we have three types of methods here. One is template based, and one is information retrieval, and one is neural network. We have some general frameworks for those different types of methods. So the first one is we have existing code and target code, and we want to find an existing code that is similar to target code, so that we can reuse the commands for and apply it to our target. And the second framework is we want to extract some structural and semantic different information from the source code by using a model, so that we can leverage those information and generate the corresponding commands. And this paper is focusing on extracting the structural and semantic information from the source code using the model. And we have different ways to represent the source code information. One of the way is use the token base, that is to regard the source code as a pure natural language, and then just tokenize the source code just like we do with the natural language. And the typical models we use is CNN and RNN. And a more popular way is the AST based. So that is to parse the source code into AST based tree structures, like the graph on the right side. So here in the graph, there is a very simple while loop and the if statement, and it is parsed into a binary tree that that represent the structure of the code. And the typical models we deal with the AST based representation is tree LSTM, tree based CNN, etc. And for the tree structure neural network that we mentioned, like tree LSTM and tree CNN, we usually, the most basic type is called the recursive neural network. And you can see the graph on the right side that if we have a tree, we have a node J, and we have the node J has two children, C1 and C2. Then the recursive neural network module will concatenate the hidden 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 units represented by C1 and C2 and times the weight and apply it by the tangent, hypertangent function. And then we get the hidden units of J.
Sorry, so here HC1 and HC2 are the hidden units of the neurons. So can you draw something about it? HC1 and HC2.
Yeah.
Yeah, draw something maybe how this neural structure looks like.
So HC1 is the hidden unit that represent the value of C1.
C1 is token.
Yes. So if C1 is token, then C1 is the then HC1 is the embedding of the C1 token.
So what is this cell count means? Oh, can you allow me to mark on the screen?
Yeah. How to do that?
I think you need to enable me to annotate.
Okay.
Okay, thanks. So what does this cell count means?
Oh, okay. This means concatenation.
Concatenation.
Yeah.
So C1 is a token, C2 is tokens. We concatenate their embeddings together and calculate HI. So why? So HJ. What does HJ means?
HJ is the hidden embeddings that represent the node J.
Okay, so you're talking about the AST.
Yeah.
AST. So AST, the embedding is calculated by its children. So that means the embedding of the parent is calculated by its children.
Yes. And the root nodes will represent the whole source code.
Understand. So
yeah, the method.
Concatenating. So will the dimension, will the dimensionality increase? So that means suppose C1 have n dimensions, C2 have n dimensions, and what dimension is this usually on this node have? How many dimensions does J have?
I think it's 2n.
It's 2n.
Yeah.
So what if it's 2n? So what if the tree is very large and once the dimensionality, it will have an explosive dimensionality problem. You can think about it. This is tree, right? So this tree is, this tree is dimension. So I'm not sure here if the number of dimensions does not increase, then that means giving the whole file, it will still have n dimensions. But that still might be okay. But I'm not quite sure. And also I have some concerns on here. So the embeddings of the parent purely depends on the children. The problem might be for each node there's a node type.
Yes.
So will the node type be I just feel that if I'm the one who designing the embeddings, node type might be also taken into consideration.
Yeah, that's the consideration of this paper.
Okay, I think there's confusion here. Maybe you can investigate more, and maybe you can keep going on about the tree LSTM and the trisom tree LSTM.
Yeah, just now maybe my answer is wrong. So the dimensionality for J is also n.
It's also n.
Yeah.
Okay.
W will be if the dimensionality of C1 and C2 is n, then the W will be n times 2n matrix. So it times a vector of 2n, then will still be the dimensionality. The resulting dimensionality will still be n.
Okay.
Yeah. So one of the limitation of this recursive neural network and tree LSTM is that it has a limit on the branch factor. That means it requires the number of children of the node is to be 2 or to be 1 or something else, because otherwise we cannot define the size of the W, the weighting parameter.
And the choice sign is that you just add all the chart together.
Yeah.
It's all took together, but the point is that the order is not considered.
Yes.
Just because the order information is lost by the sum operation.
Yeah.
Okay, keep going on.
My computer is stopped. Let me. Why?
I can hear your voice smoothly.
But I cannot move to the next slide.
You cannot move.
Maybe I stop share.
Okay, sure.
Oh wow, yeah. Oh no, I can. Let me stop share. Okay. So this paper is trying to extract information from the source code to get a source code representation and use this representation to do various tasks like program classification, defect prediction, code clone detection, and code summarization. And for this paper, it has been focusing on the program classification and clone code detection, these two tasks. And for code clone detection, we have 4 types of similar code definition. The first type is that it has identical fragments except for variations in white space, commands, and layout. And type 2 is it has variations in identifier names and literal values. And the third type is the two code are syntactically similar, but differ at the statement level. Like the fragments have statements added, modified, or removed. And the fourth type is that they are not similar, but their functionality is the same. And the paper focused on the last type of code clone detection task. So the approach of this paper is called the modular tree network, and it is to refine the basic structure of TOSEM tree LSTM by replacing a part of tree LSTM units with the neural modules designed to handle different AST units. So we can see in the graph that the leftmost part is the source code, and the middle is a normal abstract syntax tree. And their design MTN will parse this tree using so they will parse different unit of this AST tree using different neural modules. So for example, here in the graph we have function definition unit here, and they have designed a specific neural module for these units, whereas the normal tree LSTM just use all the same neural modules for different AST units.
But how about the model structure? So does the neuron, the structure, the sense, but they're using different weights, or they are?
The structure is the same.
The structure is the same. They're just using different. Okay, so they're just using different weights to learn, right?
To calculate, yeah.
Okay.
For example, for different, it had, for example, if it has 2 children, then the normal neural network will just, for the child sum, it will just sum the 2 children, and for the normal recursive neural network, it will just concatenate the 2 children. But for this MTN, with different ASD units, we will do different kinds of calculations. They have designed different kinds of calculations.
By the way, so what is the dimensionality of the vectors? So maybe or another way to ask is that how large is n?
N.
And will you please enable the notation for me?
Sure.
So anyway, we mentioned that there will be an embedding for each AST node, right?
Yes.
And when for the children's, it will, for the leaf node, we just assign embeddings of n dimension.
Yeah.
Embedding vectors of n dimension. So I'm asking how large is NUS in their approach?
I think it's a few hundred. I didn't remember.
Okay, a few hundred.
Yeah.
So given a few hundreds, will the value, given that in AST, let me think about, so the token means, okay. Okay, please go on.
Okay, so their approach is using a bottom-up procedure. So they will use the embedding of each token as the initial input, and then do various operation to get the embedding of their parents, and then finally, when it reaches the root node, so they will get a representation.
The root of the tree. The tree could be a sub-tree. The embeddings of the root of a tree is just a representative vector of the tree.
Yeah, yeah. And then they will use this vector representation to do different tasks.
Okay, please go on.
Oh, why? It's stuck again. Is it because?
Because you enable me annotate?
Yeah, I'm guessing.
Maybe you can disable my functions.
Yeah, knocking. Okay. So the MTN replaces the operation of summing up all children in child sum tree as LSTM by applying one of the designed neural modules. So here we can see that, let me annotate, this HS1 to HSNJ is the children of the node J, and they represent they are the embeddings, the hidden units of those nodes, and we apply the specific neural type for the node J, and we get the hidden embeddings for the node J, and then this but this node J, this hidden embeddings is not the final embeddings. We'll go through the same process as the tree LSTM. So the following equations from the second one to the last one is the normal calculation for LSTM for the for get gate, update gate, etc.
So what is U and W means?
U and the W. You mean here?
And I also have some confusion about XJ.
Where is XJ or XJ?
Yeah.
So here the W and the U are the parameters in the LSTM, in the normal LSTM. And XJ, XJ.
Yeah, XJ, where does this X come from? The previous.
Yeah, this one. Maybe I need to refer to the paper. Is it a type of input from the LSTM, like three of the gate, one of the gate?
So maybe that is, but I somehow lose the. I somehow can you enable me the annotation?
Yeah, yeah.
So for LSTM, so they have neurons. And then it sent it to, so more like this, right? So so for this direction, so H, this is H, right? So this is HJ. And for HJ, we just using an F to embed in it. And that XJ, maybe that is, I'm not sure I'm correct. So given XJ is something passing by, but it has already been a tree structure, so I didn't get where the XJ come from. Right, so maybe we need to investigate what the tree structure looks like. I understand we will have the H is always embeddings. When we get the embeddings, yeah, so I didn't get where, maybe you can, do you have the answers? If you don't have the answer, we can just pause.
Yeah, I don't have the answer for now.
Okay, maybe we'll pause.
Okay. Okay. So the semantic unit of C can be divided into several categories. One is the one category is that it defines logic structure and control flow information. And another one is the data information like variable declaration. And another one is the contains the calculation information like operators and variable assignments. And this paper mainly focus on the basic structure. So it has defined 8 types of modules for the C language here. And
7 kinds of nodes.
Yeah, this is 7, and the last one is the sequence. That means if we have a tree structure which has multiple children, like n children, which n is bigger than 2, but we don't know what exactly n is, then we can use this module, this sequence module, to parse the sequence of children into this module.
Okay.
Yeah. Okay, and here are some examples. The you can see the graph on the right side that this is a for loop, and it is parsed into AST tree, and the lower part is a if statement with the else, with else and without the else. So for node have 4 children, the upper part for loop, it has an initialization statement, a condition statement, and next iteration statement, and the loop body. And why the paper designed the specific neural structure like this is because the first 3 parts form the controller of the book group, and they use the recursive RNN to model them. And for the intermediate output of this unit, and for the statement of the body, they use another recursive RNN.
So here are the questions. For the child node, especially the child node is usually the tokens. And what is those in, how do we decide their embeddings?
For those tokens, they just use the normal natural language.
Normal natural language embeddings. Okay.
Yeah.
So they're using the BERT, right? They're using BERT something.
Yeah, something similar.
Okay.
And the here is a table that's showing all the 8 modules they have defined.
Okay.
Yeah.
Let's move fast to finish this presentation.
Okay.
So the key idea is that they're just using a different they categorize the AST nodes so that they're embedding this. So the idea is quite simple.
Yeah.
Okay, please go on.
And they have defined 2 types of their approach. The first type is they use the same W, U, and B parameters across all the MTN units. And the second type is that they use different parameters with different type of units designed.
So A is a traditional approach, right? A is more like a traditional approach because they share the same weights.
No. This weights is used in the LSTM.
Yes. So okay. So what's the difference?
So you can see the graph here, right? On the left graph, they have F while, F sequence. Sorry. F while, F sequence, and F if. So these are designed for different AST units, but the container, which is the LSTM, is the same. So they share the same parameters for this container. But for the graph on the right, the container also have different parameters to be trained.
So the way to but the container is still an AST node, right? It's still an
yeah.
So can you go back to maybe slide 12?
Yeah, sure.
And for these slides, maybe slide 11, or 10, sorry, it should be 10.
Yeah.
So here, there's 2 approaches. So as I understand, given a node J, so given its type, different type will share different weights, W, U, and B, etc., right?
Yeah.
And how these 2 approaches are different, and they all given W. So for the first approach, is that means whatever type it is, they share the same W?
Yes, correct.
So by the experiment, it's supposed to be the second approach is better than the first one.
Yeah.
Okay, please go on. Should be 15 now.
Okay. Okay. So they have done two types of experiments on the two different tasks. One is the code clone and one is classification. So for code clone, that it is quite simple. Just for the similar code, they assign a value of
Let's keep this
1. Yeah. And for different, they assign a value of -1. And for classification, they just after getting the vector representation, they use a fully connected layer to train the result of classification. Use a supervised learning. And here is the result for classification. And we can see that the MTB, which is the second type of approach, wins the best results, and which is also the state of the art. And on the right side, the graph showing that, sorry, the green line is not there, and the graph is showing that the MTB also converges faster than the other two types of approach.
Yeah, please go on. Let's finish this one.
Okay. And this is the result for code clone, and we can also see that it has a very good result. And for the code clone, and here is the graph showing the distribution of the similarity scores, and we can see that for the MTNB, which is the second approach, the distribution is quite consistent. And for the not that good 3LSTM, the distribution is also spread, which means the result is not very consistent.
What do you mean? I didn't get it. The accuracy, the frequency. So the frequency and the.
So the x-axis is the similarity, and the first row showing the positive, which is the similar code.
So they all looking to the similar code.
Yeah.
And for okay, so it means that the MTNB is the best, supposed to be the best.
Yeah.
Equivalent. Okay, let's get a point.
Yeah. And this is the results for the convergence during the training of the algorithm of the approach. And we can see that for both the loss function and the precision and F1, the MTN approach is much better than the 3LSTM, such that the convergence rate of the loss.
I feel that for this kind of approach, the idea or philosophy is very much similar to the Descartes, the Descartes approach, which is invented by Prof. Yihao 20 years ago. But one strength is that they're using neural net model to estimate. So maybe they can have a better performance. Maybe they have better performance, but basically they all sum up all the vectors. But the only difference is that they're using different way to sum up to compose a new vector of a tree, right? So in this case, if we have got such a tree, what do you think this approach can contribute to our common generation research work?
I think the idea is quite reasonable and makes sense that they design different modules for different types of AST units. And
frankly speaking, I think this kind of approach is very easy to attack. Very easy to attack. For example, just I will mention that unit physical is going to calculate the maximum of an array, and another piece of code is going to calculate the minimum of an array. And all we do is just change an operator. All we do is just change the operator, and whether the model can still have the same semantics, I guess not, right? So AST is just looking to whether the shape of the code looks like, but not necessarily the meanings or semantics of the code looks like.
But so, I think they can learn some semantic meanings by.
They can learn the semantics through the syntax, because AST is just a syntax. AST have no idea the control flow, and have no exact idea of the control flow and data flows. And only now there are the F block skeletons or 4 block skeletons, but it never knows that whether these variables has been used in somewhere else. But for our people to understand the code meanings, the control flow graph and the data flow graph definitely will use for understanding the code. So this code is just a shade, I think it's just some supervision. It's okay to using this approach to learn clone code, but it may not to learn some more significant amount of it. Of course, this approach can be used as well related work to learn the presentations, but these presentations may hardly use as a code generation. Very hard to use the code generation. So anyway, let's keep moving on. It's good to know that there's this kind of approach of those intermediate representations, but let's keep going on to replicate existing work, and we should have studies from our next meetings. I expect that you have already got some clone results along with their comments. We're going to check that when we have the comments and what their comments look, when they're similar kind of code, and what their comments looks like, and where there's a comments, what the difference in the comments. And also we'll let you try a little bit about MCID library. So this library will be used, I think, in the follow-up research work. Okay, thanks, Yihao.
Okay.
Thanks for the good presentations.
Okay.
And I will put the videos online. See you soon.
Sure.
Bye.
Bye.